Alright, we are going to look at the combined gas law this time. Our learning target is to use the combined gas law in calculations to solve for either pressure, volume, or temperature. Alright, a little reminder here of our gas laws. Our Boyle's law review. As the volume goes down, the pressure also goes down. As the volume increases, the pressure goes down. So it means, if you look at this picture here, higher pressure, smaller volume. Lower pressure, as that piston comes out, we have a larger volume. They go in opposite ways. That's Boyle's law. Then, if we look at Charles' law review, as our temperature drops, the volume also drops or decreases. As the temperature goes up, the volume also goes up. These ones we call a direct relationship. They go in the same direction. Okay, and our Gay-Lussac's law. As the temperature drops, our pressure also drops or decreases. As the temperature goes up, the pressure also increases. Now, for our combined gas law, we are going to actually combine them all together. And just like all of our other gas laws, all temperatures must be in Kelvin at all times. So if they give it to you in Fahrenheit or Celsius, we have to convert them into Kelvin first, or it will not work. It does not work if you've got a 0 degree or a negative temperature. We get some really funny results that do not work out at all. So our P1V1 equals P2V2 combined with our V1T1, V1 over T1, and our V2 over T2 to get this purple equation, which is your combined gas law. Pressure 1 times volume 1 over temperature 1 equals pressure 2 times volume 2 over temperature 2. They'll give you usually, pretty much always, 5 of those 6 variables. We have to solve for the 6th one. Let's take a look at an example of one. Alright, combined gas law practice. Now, for most people, the trickiest thing is trying to break down which of the 5 do we have, and which of the sixth one are we missing. So a 40 milliliter sample of helium gas is collected at 298 Kelvin. It's in Kelvin, so we're good there. And 3.3 atmospheres. What volume would this gas occupy at standard temperature and pressure? I don't know what those are. Okay, so 40 milliliters, that's a volume. Volume of helium gas is collected at 298 K, which is our temperature, and 3.3 atmospheres. So we've got one volume, one temperature, one pressure. What volume? They're looking for a new volume. Will this gas occupy if it's changed to STP? Get out and go, well, I don't have enough stuff. I don't have enough variables. What you do, you have standard temperature and standard pressure. You gotta remember what those are. So if we look, we know our volume 1 is 0.4 liters. They have to be in, I don't have to be in liters, they have to be the same. Our temperature 1 is our 298 Kelvin. Our pressure 1 is our 3.3 atmospheres. We have everything in our initial ones, in our first ones. We don't know the volume because they say what volume, so we know it's unknown. Temperature 2, we know is 0 degrees Celsius, which we can then add 273 to get us in Kelvin. And pressure 2 is 1 atmosphere. We want it to match the same unit as our other pressure, which is 3.3 atmospheres. We now have 5 of the 6. We can do our work to get the other one. So we know all of our 1s. P1, V1, and T1, we'll plug them in. P1 is 3.3 atmospheres. P2 is 40 milliliters, which would be the same as what up here is 0.4 liters. Whatever unit we put in for pressure in the equation will be the same as we get on the other side. Same we put in volume of liters, we'll get out liters. We put in milliliters, we get out milliliters. And our temperature 1 is in Kelvin. So that one is the one that definitely has to be in Kelvin. You can't pick and choose what unit to use. So we know P2 and we know T2, so we'll put those in as 1 atmosphere and 273 Kelvin. volume 2 is what we're solving for. So we've got 5 of these. To solve this, we have to get volume 2 by itself. It's not too bad since volume 2 is on top. We're going to have to cross multiply in our next step. So when we cross multiply and divide, we get these 3 multiplied, and 298K times 1 atmosphere will be the ones on the opposite side that we then divide out to get gone from the volume 2. And when we do that math, we get volume 2 equals 0.121 liters. If that's confusing, you want to draw a little more detailed, let me know, I can show you in person. Okay, our second example here says we have 350 milliliter sample of helium gas, and it's collected at 22 degrees Celsius and 99.3 kPa. What volume will this gas occupy at STP? I give you a little hint at the bottom. If you think you can do this, go ahead and pause it. Either way, give it a shot, see where you get stuck if you can't do it. So when you think you've got it, or you're stuck, hit play again. Alright, so, again, write down what variables we have, which ones we know, which ones we don't know. Right, we know volume 1 is 350 milliliters, which would be the same as 0.35 liters if you convert it. We know temperature 1 is 22 degrees Celsius, which we know is going to have to change to Kelvin. Pressure 1 is 99.3 kilopascals. Volume 2 we don't know because they're asking for it. Temperature 2 is 273 Kelvin because that's standard temperature, 0 degrees Celsius plus 273 Kelvin. And pressure 2 is 1 atmosphere. So, notice that our units of temperature right now are not the same, and our units of pressure don't match up. First step, we have to get our temperature into Kelvin. So to do that, we have to add our 273 to it to get to Kelvin. Second step, we have to change our pressures. Now these, there's no set pressure it has to be for our combined gas law. So we could either take pressure 1 and turn this one into atmospheres, or we could take atmospheres and turn them into kilopascals. I like atmospheres as just my go-to unit, so I'm going to turn pressure 2, sorry, not turn pressure 2, I'm going to turn pressure 1 into the same unit as pressure 2 into atmospheres. So now we got this here again. Convert Celsius into Kelvin. Like I said, add 273. Now we've got T1 is 295 Kelvin. Second step, do our one-step conversion. Should be easier than stoichiometry. And get 0.98 atmospheres for pressure 1. Awesome, they're now in the same unit. Always go back if you need to. Now we can solve. They're all in the same units. Awesome. Plug in the things we know. P1, V1, T1 equals P2. V2 we don't know. We'll solve for that. T1. Again, I know you got two things equal on different sides. Cross multiply and then divide. So we'll take 0.98 atmospheres times 0.35 liters times 273 Kelvin, and then that'll be equal to 295 Kelvin times 1 atmosphere times V2. Once we've done that, then we need to divide by the things that are tied up with our V2. So divide by 298 Kelvin and divide by 1 atmosphere. Our units should cancel out like that. Take a look, make sure you can see those being canceled out. And then we're left with just liters on this side for a unit. And just volume 2, which should make sense, right? Volume 2 should be a volume unit. Liters is a volume unit. That's what we want. When we do the math, we get 0.317 liters as our volume. Voila, there you go. That's all there is to it. It's just follow your units, make sure they're in the right units, make sure temperature's in Kelvin, cross multiply and divide, and you're good to go. If you got trouble with it, let me know. I'll give you a hand. Otherwise, try some practice ones.